Last time we learned that Newton's laws lead to a differential equation. If we have a differential equation, how should we numerically approximate its solution? To answer this question, let's go back to our example of the spring and damper, which I'm sure you're getting sick of by now. The differential equation, as I'm sure you remember, is x dot equals minus k over b x equals f of x. Now it's helpful to rewrite this so that the time dependence is explicit. So we have x dot as a function of t is equal to minus k over b times x as a function of t. I'm rewriting this so that you can specifically see that x depends on time. The position, therefore, is allowed to change as a function of time. Moreover, I'm going to refer to the right-hand side of the differential equation as f of x of t. If we now look at the left-hand side, we see that the derivative of x of t with respect to t, which by definition is equal to x dot is equal to the limit as dt goes to 0 of x of t plus dt minus x of t all divided by dt. That's just the limit from calculus that you've learned previously. So far, I haven't changed anything. This is still a differential equation, and it is still equal to f of x of t. However, if I do not take the limit and instead simply say that dt is some rather small number, where I'm not going to say exactly what I mean by small, we get an expression that only approximates x dot and is therefore approximately equal to f of x of t. If I rearrange this approximate equation, I get that x of t plus dt is approximately equal to x of t plus dt times f of x of t. This formula, called Euler integration, means that if we know x at some time t, we can approximate x at t plus dt. This also means that you should expect to need to know x at some time in order to get the algorithm started. Euler integration is the easiest method for numerically approximating a solution to an ordinary differential equation, but there are certainly other options. You will see in homework that sometimes Euler integration doesn't do a very good job, but if you make dt small enough, you will always end up approximating the limit in the definition of the time derivative well enough to give you a decent approximation of the solution to the ODE. To practically see how Euler integration works, let's look at the spring damper system again. We know that x dot is equal to minus k over b times x, and that therefore x of t plus dt is approximately equal to whatever x of t is plus dt times minus k over b times x of t. If we then assume that we know that x of 0 is equal to 0.5, and we know that k is equal to 1 and b is equal to 1, then we can approximate x at 0.1 by 0.5, that's x at time 0, plus 0.1, that's dt, times minus 1 times 0.5. That's equal to 0.45. Now, if we wanted to approximate x at 0.2, we could do the same thing where now x at 0.1 is equal to 0.45. Then we add dt times minus 1 times 0.45 again. And here we get 0.405. We could continue this process for x at time t equals 0.3, x at 0.4, and x at 0.5, and so on. In case you haven't guessed, this process could get really annoying over time, so this is why we have a computer do it. Let's look at two pieces of code, one in MATLAB and one in Python, since those are the two choices you all have to use. Both pieces of code implement Euler integration for the spring damper system. Note that at the top of the code, we declare the initial conditions to be x of 0 equals 0.5, that dt is equal to 0.1, and that k equals 1 and b equals 1. Then we create an array to store all the variables for all time. Then a loop executes Euler integration and stores the value in the arrays. After exiting the loop, we plot the results. You will do code very similar to this in your homework assignment, so looking at this example several times will be helpful. What should you remember from today? Euler integration provides a means for you to approximate the solution to an ordinary differential equation, and it doesn't matter whether the differential equation is linear or not.